Good morning. Here we are yet again for another lovely session of CENG 4412 Steel and Concrete Design. This is going to be the 19th lecture in the video series, and today we're going to begin our discussion of concrete column design. So this video is going to be on short concrete columns, and I wish to describe the difference between, in this video I have a few objectives. First, I want to describe what a short concrete column is. I wish to discuss the difference between tied and spiral concrete columns, and also look at how to calculate the capacity of a short concrete column. Okay, so let's consider this. So the topic for today is short concrete columns. So what is a short concrete column? Well, the basic idea is that a short concrete column, a short column in the concrete sense, is one that does not experience substantial moment. That does not experience substantial moment or buckling. Well, actually, I should probably separate these out and say a short column is one that does not experience buckling. In other words, we're under our buckling capacity. And also, typically, and when I'm talking, usually when I consider short columns, I'm considering columns. Today I want to look at calculating columns. Today, at least, I want to look at calculating capacity. Calculating the capacity of columns with no moment applied. I should probably say the capacity of short columns with no moment applied. So, in the case of concrete columns, this is actually very difficult a very difficult state to achieve. Now, with concrete columns, I want to break this down between these two different topics: short columns versus no moment columns. Short columns, unlike steel, are actually fairly easy to achieve. This state is actually fairly easy to achieve. Because these again are columns that do not experience buckling, because of the very large cross-sectional areas. The large cross-sectional areas of concrete columns, of concrete members. Buckling is often not controlling. Often buckling does not control. Or often crushing rather than buckling does control. So for example, if you look at a steel member, for a steel column to carry this, let's look at a steel column versus a concrete column. To carry a certain vertical load, a steel column might just be something like a HSS shape, something like this, a very thin-walled hollow square tubing shape. But to carry this very same axial load, you might need a very, very large, quite solid concrete section. Instead of a small hollow square steel tube, you might have a quite solid concrete block or concrete column. Maybe something like we could look at the exact capacities, but you know from experience that concrete columns are going to have a much larger surface area, a much larger cross-sectional area for the same strength as compared to steel columns. So again, because of large cross-sectional areas, because of large cross sections, concrete columns tend to have large moments of inertia. Have very large moments of inertia. Thus, they are more resistant to buckling. That does not mean you can't have concrete columns that can buckle. We refer to those as slender concrete columns. So again, our general regime here is going to be that for for a certain length here, for a given cross section, as you go along, below a certain length, it's going to be short, a short column, and above that length, it will be a slender column. So for given the cross section, if you make a very short column out of it, if you don't make a very tall column out of it, then that's going to be what we refer to as a short column. But as you start making this longer and longer and longer, taller and taller and taller, eventually the same cross section becomes what we would refer to as a slender column. Next, I want to talk about concrete columns and moment. In most cases, concrete columns will actually experience moment. We discussed moment let me describe this first. In most cases, concrete columns, in fact, let me put a little title here, moment. Concrete columns and moment. Almost all concrete columns are beam columns. And what I mean by that, of course, is that they will experience, in almost all cases, they experience both moment and compressive stress. In almost all cases, they experience both moment and both compression and flexure. They experience both moment and flexure, compression and flexure. So in most cases, we will have to consider moment and axial force interaction. Moment compression interaction, or moment axial force interaction, and we'll discuss this later. This is something I'm going to cover in the next lecture, in the next video at least of this lecture. That is our moment and axial force interaction diagrams, which we'll discuss later. But why is this? Why are concrete columns more susceptible to moment than steel columns are? Well, fundamentally, it comes down to two reasons. Why? Well, one, the cross sections are again larger, thus increasing the chance of having a eccentric loading. Thus increasing the effect of eccentric loading. Of eccentric loading. So for example, let's say you had a 12-inch by 14-inch concrete column. Maybe even a 16-inch by 12-inch concrete column, big old concrete column. And so this is looking down from plan view here. But then if I look at this in elevation view, let's say that I have this concrete column here. And then I have resting at its edge, let's say perhaps I had a beam resting on it like this. Now that's not how you would actually build that is of course not how you would actually build a connection, but the way you actually connect columns and to beams is actually going to contribute further to the moment, which is something I'll go into in the next slide. But look at this diagram here. Consider this diagram. Where is the center, how is the force actually being transferred down into that column from the beam? So if you look now, if we treated this just as a naive pin connection, ignoring the actual rebar development lengths and things like that, at that connection, this thing is going to be distributing force down and stress down like this. There'll be an area here. But where is the centroid of that force? The centroid of that force is actually right here. The centroid of that force is actually right here. So in this particular diagram, as I've drawn it here, the centroid of the force would actually be about there. So the larger your section, the larger this offset moment arm. So if you have the centroid of the force offset from the centroid of the member, this is effective. You have a force, you have it off at a distance, you now have a moment arm. So this is your offset. This is like a D here. And so you have columns. So your column here will be experiencing a force F, but it will also be experiencing a moment FD. This is the effect of this again is the effect of offset loading. This is eccentric loading. So that's not to say that you could not just build this beam all the way over the column, but the larger the cross section, the more vulnerable it is to eccentric loading, simply because any offset will be magnified just by the much larger moment arms present in the dimensions of the member. The other reason why is because of the concepts of development length. Two, so again, we're looking at reasons why concrete columns almost always have moment. Two, almost all concrete connections by their nature do transmit some moment. So we'll still have we will still have what we call moment connections and shear connections. We'll still design to have what we call moment and shear connections. But almost all concrete connections inevitably transmit some moment, even just in bearing. But almost all concrete connections do have some moment capacity, even if it is only in bearing. Even if just in bearing. Okay, so that's just some brief theory, introduction, that sort of thing. So that's why I want it. So I just wanted to give you these definitions of what a short column is, and why also, and give you some appreciation, hopefully, for why most concrete columns will in fact actually have moment. Today we're going to be looking just at the concrete columns that don't have moment, so short concrete columns without moment applied. But I'm going to be describing that, but I want you to keep in mind that this is kind of an edge case. In most cases, you are actually going to have some level of moment, and we need to use what's known as a moment axial force interaction diagram, and we will learn about that next time, or perhaps in the next video. Okay, so and in addition to classifying columns by length, another way of classifying concrete columns is by geometry. Concrete column geometry. There are essentially two main families of concrete columns. So here, and these are tied and spiral columns. You may have heard of these before. So we have tied columns and we have spiral columns. And really what these come down to effectively is, well, more or less, not exactly, but more or less, circular versus square cross sections, although there is a slight difference in how the reinforcement is laid out. So here, tied columns and spiral columns. So tied columns generally will have a square cross section in almost all cases, or square or rectangular, I should say. So here would be, so let me just draw out what the insides of both a tied and spiral column would look like. Then I'll show the forces applied. Both of these would be experiencing some sort of axial force, P and P, P and P. Now, then the internal reinforcement of these is one of the major differences between these. Well, first, actually, let me show the cross sections. Maybe this would have a rectangular or square cross section. And this would generally have a circular cross section. And here, then I'm going to show the rebar. Maybe I'll show it in bright orange because, you know, of course, everyone makes their. It's standard in construction to make to use bright orange rebar. I don't know about you, but I only use bright orange rebar. Of course, that's very typical.
Epoxy coated.
I guess it could be epoxy coated. That was a very, very bad joke, but yeah, not the epoxy coated, the bright orange. But I guess it's too early in the morning. Okay. Anyway, so very poor structural engineer humor. Okay, so here the rebar is just going to look something like this. Here the rebar cage will just look like this. You have major bars going up longitudinally, and then you have ties periodically sort of giving this thing a ladder appearance from the side. And the reason this is referred to as a tied column is because it really is sort of just tied down. You have your major axial reinforcement, and then you have a tie going all the way around, similar to the idea of shear stirrups, although not exactly the same thing. You have just ties working their way around, just a piece of number 3 or number 4 bar wrapping its way around the section, providing confinement and helping to prevent buckling. But then with spiral columns, it's going to be something a little different. So first of all, you're still going to have your major axial reinforcement like this. And from the top, the spiral doesn't really look that different than the tie, except, well, I cannot draw a circle today. I have my potato column here. Perfectly circular. Isn't that lovely? Anyway, then I'll have my major axial reinforcement here. But it's called spiral for a reason. It is not simply, spiral columns are not simply this, but in rectangular, but in square mode, but in circular mode. You do not simply have circular ties. Rather, you literally have a spiral of reinforcements. It's spiraling its way up like this. A helix, basically. Usually it's better. Usually it's more better. Usually it's fabricated better than I've drawn here. Usually, sometimes not, but anyway. So tied versus spiral. Let's discuss the benefits and drawbacks. Tied versus spiral. Now, here, these are in fact more common. They're approximately 95% of all columns constructed. Why would they be more common? Any idea? Why would spiral columns be more common?
The continuous rebar. You just cut it once.
you just sort of cut it once. Yes, you don't need that continuous rebar. Well, more actually, probably a lot of it probably just comes down to the cross section. It's intrinsically easier to make something that's a rectangular in shape than it is to make something round in shape. That's one of the major reasons for it. But also the ties may be easier to work with than the large spiral cages. But anyway, however, it's not as effective at containing the concrete. So while they are more common and easier to construct, they are not as effective at retaining concrete or confining concrete. What I mean by that is preventing spalling, preventing loss during high loading events, seismic loading events, whatever that may be. And then spiral columns. These are used especially in seismic regions. In seismic regions, they have good strength in all directions. And they have higher ductility. They have higher ductility, which is useful for, especially for seismic regions, seismic loading. Oh yes, pardon my terrible handwriting, that's good strength. It looks like a 6, okay. Okay, next I'd like to show sort of a capacity, a little graph of load versus strain. Load versus axial shortening for tide versus spiral. Just a sort of general graph here. Load versus axial shortening. Load, axial shortening. So let's look at, let's look at tide versus spiral. And this would be a plot of a short, no moment column. So for something like, first I'll plot out something like a tide column. So both of these initially are going to start out relatively linear. Maybe actually more like this. But then it will have more, this is going to be the tide column, and it's going to fail in a more brittle failure. So this would be the tide column. Low ductility. Again, we remember from mechanics of materials, what is ductility? We remember from mechanics of materials, what is ductility? Exactly. Yes, of course. The ability the measure ductility, of course, is the measure of any member's ability to absorb deformation prior to fracture. So, tide columns will have low ductility. They'll have a range. They're elastic. They'll get a little bit of strain hardening, and then they'll just fail. They are relatively low ductility. Here. But then with the because of this, but then also looking at the let's next look at the spirals. The spirals, because of they're better able to confine the concrete, they are going to have this kind of, they basically allow, it's, okay, in terms of why they more effectively do this, well, they sort of lock the concrete together much more effectively. This allows more of a 3D stress state to develop, and this in turn produces a greater ductility. So, in comparison, they're going to be something more like this. This is where the spiral breaks, and this is a spiral column. So spiral columns, again, high ductility. And this would be where the shell spalls. Okay, so because of this, we know that generally brittle failures are more risky than or more dangerous than ductile failures. So because of this, this comes back to the basic. This behavior tells us why we have different feed factors for these two types of columns. So for at least for compression controlled sections, for spirals, phi for our tide is going to be 0.65. So for, maybe I'll mention these are for compression controlled sections. Or just maybe down here. For compression controlled columns, in other words, where just the compressive capacity controls, not moment, the phi for spirals is going to be 0.75. While the phi for, the resistance factor for tide columns is going to be 0.65. So again, we know that brittle failures are much more devastating than ductile failures. Why is that? Why would we prefer a ductile failure to a brittle failure? Why is that?
Because it's absorbing energy as it fills.
Exactly, because it's absorbing energy as it fails. It's deforming quite a bit before it fails. And what that really gives you is what? That gives you notice. That gives you, if you notice that the beam is really deforming a lot and that it's cracking and it's deforming and it's bending really strongly, that gives you time to say, okay, well, if this thing is having some sort of ductile yielding failure here, I'm going to make sure I'm not standing underneath the thing when it finally fails. So ductile failures generally give you time to evacuate the structure, to get out of there. They are always going to be a less critical or less dangerous than brittle failures. Brittle failures are just sudden, without warning, just like a pane of glass shattering. That is a brittle failure. A ductile failure is, well, if you want to think of a extreme ductile failure, think of silly putty, although, of course, hopefully your building is not behaving like silly putty, because that would be very terrifying. But anyway, so as we mentioned, concrete columns are almost always going to have some amount of axial force and moment, but anyway, and they can be short or slender, and we've already defined that. So let's look at the strength of short concrete columns. Here, let's look at the short strength of here. The strength of short concrete columns without moment. The strength of short concrete columns without moment. So, this is going to be fairly simple. For a concrete column here, that is, again, we're looking at the condition, so a short column, that means no buckling. No moment, well, that means we only need to consider axial force. And because of that, we really just have to look at two things. There are two factors that are going to contribute to the strength of the column here. So if you look at a concrete column, the ties won't contribute directly to the strength of a short column. Those are absolutely critical for the longer columns or columns experiencing moment. But for short columns, the only thing that really matters is the longitudinal reinforcement and the concrete section. So basically we have two things contributing strength. The ultimate strength, the effectively sort of the phi Rn, or whatever you want to call it, the strength, the phi Pn, or just the Pn, or maybe Rn, nominal resistance, is just going to be the strength of the steel The strength of the steel plus the strength of the concrete. Strength of concrete. So what this means then, that's a really weird equal sign. This would come down to basically the area of steel Fy, plus 0.85 F prime C, 0.85 F prime C times the area of the concrete, or area of steel Fy, basically the yield capacity of the steel, plus, and for the area of the concrete is going to be fairly simple. It's just the gross area of the section minus the area of the steel. So 0.85 F prime C times the gross area minus the area of the steel. The gross area minus the area of the steel. And the code approach here, so that's the sort of theoretical way to handle the actual nominal capacity of these things. But on the next slide, I want to go into the I want to go into the code approach. Okay? The code approach here is to say that for tied columns, here's what you'll find in the manual. First, we're going to have a couple, two factors, 0.80 and 0.85. These aren't actually your phi factors. These are basically, let me put phi RN, the design capacity. Phi RN. Here for the tied, it's going to be 0.80 and 0.85. And then times phi, and then times the sort of theoretical capacity, 0.85 F prime C, times the gross area AG minus the area of the steel AST, plus Fy times the area of steel. Fy, or let me just say AS instead of AST. Fy times AS here. And this is going to be the same thing, 0.85 F prime C times AG minus AS. Basically, this is just a way of calculating the area of the concrete. Plus Fy AS. And let me annotate this a bit. First of all, I want to mention this first factor, the 0.85 and the 0.85, this here. This is not necessarily a phi factor. What this is that what this fundamentally is something to take into account that almost all columns, even those that we call short columns, even if our math says that they're not going to have any moment on them, we generally say, okay, in reality they're going to have some moment on them, so we're going to decrease the capacity a little bit. So here, this is a reduction factor, a slight reduction, to take into account that all columns have some moment. Since all concrete columns carry some moment. All concrete columns carry some moment. The phi, of course, is just going to be your strength reduction factor or resistance factor. Your resistance factor. And all of this here, again, is just sort of the theoretical strength of a short column the theoretical strength of a short column in crushing. Theoretical strength of a short column in crushing. That is on, I need to get the citation for that. I need to check that. Anyway, so here, theoretical strength of a short concrete column. In crushing. And in a later video, I want to go through. So these are found in the manual. And what I want to do later is in a second video, I want to come back later today and sort of go through a more code section by section approach to handling concrete columns. But that's the base equation that you'll see for short concrete columns. And that one's easier to explain here because it's just a brief introduction to crushing in the capacity of. And the nice thing about this one is you can find this. You can figure this one out just from basic, very simple mechanics, materials theory, that sort of thing. All right, any questions on this? All right, so that'll finish it for that portion of the lecture. Just wanted to cover a brief introduction to concrete columns, why concrete columns always have a moment applied, what a short column is, etc., and how to calculate the compressive capacity of short concrete columns.